Welcome back to another session called Convolution. We're on convolution. In this particular session, we're going to convolve a unit step with another unit step. We continue to have the same definition of the convolution. That's not going to change. We have our two waveforms. Typically, h of lambda might represent an impulse response of a system, and x is the input to that system, where x is a general input. But in this case, we're going to apply two specific waveforms or functions for those h's and x's, and in particular h, we are going to allow that to be a unit step, and the input x, we're going to have that be a unit step also. And what we want to do is find the result in output when our system has an impulse response that's a unit step and we apply a unit step to that system. Here's what we have then. We have y of t is h convolved with x, where h and x are both these unit steps, or when the argument of h and x, whenever that argument is positive, then the waveform assumes a value of 1, and when it's negative, it's 0. And in particular, I should say when the argument is non-negative, it's 1, and when it is negative, it's 0. What I want to do in this video is really address four different things. First is sort of a background thinking, what's going on. Then we will evaluate this integral three different ways, or this concept will solve three different ways. We'll do it in the time domain on the first two, where we will evaluate the integral, the convolution integral, analytically. Then we will evaluate that same integral, but then we'll do it graphically. And then in the third evaluation procedure, we will do it not in the time domain, but in the frequency domain. Just a little background to get us thinking what's going on. What is actually going on physically when the unit step is convolved with the unit step? Another way of asking that a similar question is, or is there a system that might have a unit step as its impulse response? Or is it possible for the impulse response of a system to actually be 1 for non-negative arguments of the independent variable, and 0 whenever the independent variable is negative? If I didn't have a good answer for that, I probably wouldn't have asked those questions, and we could have stopped the video, or we wouldn't have even had to address this video or this concept. But the answer is yes, and one system that we can create, and you can actually build this with an op-amp and a capacitor and some resistors, is to go ahead and look at a system that consists of a pure integrator. In block diagram form, here is our system. Again, we usually have our inputs on the left and our outputs on the right. Our input, let's say, is x of t, our output is y of t, and what we want our system to do is take this input x of t, whatever that is, and integrate it up to time t and generate the result, which will be our output. So now what we want to do is say that our system is just this integral or integration operation. If that's the case, if our system is just a pure integrator, what is the output which we call y of t conventionally, when the input, and again we're assuming our system now is a pure integrator, what is the output of that pure integrator, or what is y of t when the input to that pure integrator is x of t equal to delta t, where delta t is the notation I'm using for this impulse waveform. That's this infinitely tall waveform that happens only at, or happens between, let's say, t equals 0 minus and t equals 0 plus, and the area underneath that waveform, if you were to integrate it, is 1. So let's look at what we have here. If our system is an integrator, what happens when we actually apply an impulse waveform to an integrator? And now we just have to remind ourselves of what really is happening when we integrate an impulse waveform. But we can think of that notationally as saying, okay, we want to know what is y of t if this integration operation, which takes some integrand and integrates it, well, what if that integrand is actually the impulse waveform? I hope you can see that the output, the y of t, is going to depend on when or at what time we are interested in evaluating that integral. So let's look at the upper integral, or upper limit, of this integral to try to interpret what y of t is going to do. Suppose we look at, or say for t less than 0, if the upper limit of our integrator is less than 0, what's actually happening with this argument? Well, for t less than 0, this impulse function, and now this t is what we are integrating up to relative to this variable of integration lambda. If our variable of integration lambda has not even reached 0, then what's happened to our argument of the integral? Well, if we're still upper limit of integration t, if that's less than 0, then the impulse waveform delta of lambda has not even turned on. And if it hasn't turned on, then it's 0, and we integrate 0, and what do we get? Well, we have 0 coming out of an integrator if we have 0 being integrated, which says that y of t, our output of that integrator, is going to be 0 when the impulse is the input to that integrator. We're going to get an output equal to 0 when t is less than 0. So that's the first range on our upper limit. If we say, well, let's look at what happens when t is non-negative. When t now is going beyond 0 plus, then delta of lambda has actually turned on or occurred. The impulse has happened, and that happens at this variable of integration right at lambda equals 0. And if the impulse has happened underneath an integrator, then the area underneath that integral, or underneath that impulse waveform, delta lambda, is 1 by definition of the impulse. Which now, that says that y of t, when the upper limit t is bigger than 0, greater than or equal to, and we are evaluating this integral, then that's going to be 1 for t greater than or equal to 0. Or we now have y of t is equal to 1 for non-negative values of t. And that's now giving us what we wanted. Now we can see that the impulse response, or h of t, for a pure integrator, if our system is just an integrator and we apply an impulse waveform to that integrator, then our impulse response of that system, which is a pure integrator, is simply going to be 1 when the time, or the independent variable, is non-negative, and it will be 0 when it's negative. But this behavior is just the unit step function, or u of t. And now we know what we can think of conceptually if somebody says, oh, we have a system whose impulse response is the unit step. Well, that's like saying you have a system that is just a pure integrator. Let's now evaluate that system, a pure integrator, when we apply to it an input that's a unit step. And we're going to solve this now 3 different ways. Let's do it first analytically with just our integration definition. So maybe I should say the analytical evaluation. I wanted to say evaluation analytically, but now we have this unit step, and that's the impulse response of our system, which in this case we know that that's the impulse response of an integrator. And we want to convolve that with another unit step, which would be similar to thinking, well, we're just going to apply a constant to that integrator, where the constant switches on at the origin. So this is a constant value of 1 for non-negative values of the argument t. Let's now evaluate what the output of that is going to be. Here's our convolution integral, and now we have the impulse response. Well, I'm not writing what I'm hopefully saying. Hopefully I said that this was the impulse response of an integrator. Our impulse response is now this unit step. Let's call that u of lambda. We then have the input of our system is what we flip and slide, so we now have u of t minus lambda, and we integrate that with respect to lambda. What we want to do is recognize what the unit step does relative to its argument and play with that, or use that to our benefit to evaluate this integral. And the first thing that we can do is, let's look at this piece. This is really just a switch that's either 0, or a waveform that's either 0 or 1, and it's switching when the argument lambda is 0. or the note that I want you to keep in mind is that this waveform that we've identified by this underscore of 1 is 1 for non-negative values of lambda, and it's 0 for negative values of lambda. Well, what are we integrating with respect to? We're integrating with respect to lambda, and that lambda is varying between minus infinity and infinity. But what we've just said is this particular piece of the integrand is only going to be 1 when its argument lambda is non-negative, which says that all of these negative values in the integration are not going to matter. And another way of writing that or stating that is to say that now the lower limit of integration in this output expression we can simply make that 0. So the lower limit of integration can be made 0, and this waveform in our integrand, this u of lambda, can now be set equal to 1 because we've now turned it on, and by turning it on we've changed the limits of integration, and now our y of t convolution integral has simplified a little bit. It's now this integral from 0 to infinity, and now we have this 1 replacing u of lambda, and we have what we had before, u of t minus lambda d lambda. We've now simplified that integration formula by getting rid of essentially this time interval from minus infinity to infinity by realizing what u of lambda is. It is a waveform that turns on at non-negative values of lambda, and that allows us, because that's what we're integrating with respect to essentially establish the lower limit of integration as 0. If we now look at the remaining argument in our integrand, u of t minus lambda, that's a unit step which has an argument of t minus lambda. By definition then, that's going to be 1 as long as its argument is non-negative, and it's going to be 0 as long as its argument is negative. Well, we can rewrite that by simply saying, well, that's 1 as long as lambda is less than t, simply by adding lambda to both sides. Or if that's, we can simply write that a different way and say, as long as lambda is less than or equal to t, which is what we're saying there, then this argument of our integration is going to be 1, and for all the other values it's 0, or when lambda exceeds t, then we're going to basically have, we will have a value of 0 for that waveform. Now, what are we doing? We're integrating, we're plugging in a particular value of t and evaluating this integral. If you think about that now, lambda is our variable of integration, and we now are going to be able to replace that upper limit of integration in our expression for the output. That upper limit of integration can be set equal to t because anytime lambda is bigger than t, if lambda, our integration variable, exceeds t, then this argument, this integrand, u of t minus lambda, becomes 0. Because of that, we can set the upper limit of integration, set that equal to t, since lambda greater than t, or maybe I should say since when lambda is greater than t, the integrand which is u of t minus lambda, that actually equals 0. And what else can we do? Well, we can now replace u of t minus lambda with 1. So, and the second point then, making this observation, is that the integrand u of t minus lambda can be set equal to 1. And that is because, or since, the step function, which is what u of t minus lambda is, the step function u of t minus lambda will equal 1 for values of lambda between 0 and t, meaning when, or that is, the argument of u of t minus lambda, which is t minus lambda, is positive when lambda is less than t. If that's the case, now we can rewrite this expression. We started with the lower limit of 0. Now the upper limit can be set equal to t. The first observation was that the u of lambda was 1. Now with this upper limit set equal to t, we now know that this second u of t minus lambda integrand term is 1. And now we have that integrand, which is just 1, integrated with respect to lambda. Well, if we integrate a constant, we just get lambda, and we evaluate that from 0 to t, and we obtain t for our output. And so now, if we apply a constant that turns on at the origin, and it has an amplitude of 1, if we apply that to a pure integrator, we're simply going to obtain a ramp with respect to time out of that system. And so the result of applying or convolving a unit step with another unit step is to create this ramp waveform as a function of time. Let's now do this integration graphically. Here's then a graphical evaluation. We have again y of t is this integral from minus infinity to infinity of u of lambda, u of t minus lambda, d lambda. Well, we have u of lambda in a couple of places. We have u of lambda just by itself. That looks like turning on at 0 at lambda equals 0. Then we can look at flipping and sliding that, and we need then to do this in a couple of different steps. We can say, okay, here's u of minus lambda, and then finally u of t minus lambda. Again, our variable of integration as lambda is now this waveform that we will now use t, this adjustable parameter t, to slide u of t minus lambda through u of lambda. Let's now look at the overlap patterns that will allow us to perform this integration. The first overlap pattern, like in the past, is the no overlap case. In the no overlap case, then, pictorially or graphically, here is our u of lambda, and here is our u of t minus lambda. They both have amplitudes of 1. Here is u of lambda. Here is u of t minus lambda. Our independent variable is lambda. This overlap pattern is true or exists or occurs as long as we keep t less than 0. And if t is less than 0, this interval of support does not overlap with that interval of support, and we end up with y of t is equal to 0 as long as t is less than 0. That's our first overlap pattern. Our second overlap pattern is when we start to move u of t minus lambda through lambda equals 0, and I'm going to emphasize this diagram by slightly adjusting my amplitudes, but those amplitudes are still what we know them to be. They're still of value 1. Here's u of t minus lambda. Here's t. Here's the interval of support for u of t minus lambda. Here is the interval of support of u of lambda. This particular overlap pattern is going to be true or occurs when t is greater than or equal to 0. And the result, the output, is now going to be the limits of integration. I'm going to integrate from 0 on lambda up to t, and I'm going to have u of lambda, which has a magnitude of 1. I have u of t minus lambda, which also has a magnitude of 1, integrated with respect to lambda. That's now just lambda evaluated at 0 and t, and that now becomes t for t greater than or equal to 0. Therefore, by doing the evaluation graphically, we found that we have y of t, our output, giving us a ramp of slope 1, so we have t for t positive, non-negative, and it's 0 for t negative. We've now done the evaluation two different ways in the time domain, analytically and graphically. Let's now look at evaluating this convolution of 2 unit steps in the frequency domain, which I will just say, let's do some frequency domain analysis. Doing that, what we have in the time domain again is y of t is h of t convolved with x of t, where h is our impulse response, x is our input. we can think of that in the frequency domain as now a multiplication of the transform of h of t, which is capital H of s, and the transform of x of t, which is capital X of s. If we find capital Y of s, then we can obtain the time domain result by simply inverse Laplace transforming the Laplace transform of our output. What we want to do then is look at this when h of t is the unit step. If that's the case, then this transform of u of t, the Laplace transform, becomes 1 over s, and this now, 1 over s, you can think of as a system. This is the frequency domain representation of an integrator. So this system is an integrator. If we were to go back into the time domain, an integration in the time domain corresponds to an operation of division by s in the frequency domain. We also have x of t, our input, is also a unit step. This is a signal, so this was our system, and that was the system's impulse response. This is our signal, and the signal that we're applying to the system is a unit step, and the transform of this unit step is 1 over s. And now this frequency domain expression, 1 over s, can be interpreted differently than the 1 over s above. This one now is saying that the input is a unit step in the time domain. And if we Laplace transform this waveform of a unit step, we end up with 1 over s in the frequency domain. Now this allows us to find the answer fairly quickly. We know that the output y of s is just the product of the two transforms, h of s and x of s. H of s had a transform of u of s. X of s had a transform of u of s. Each of those had a 1 over s, or we're now seeing that the output Laplace transform is now 1 over s squared. If we want to obtain y of t, the time domain answer, we need to inverse Laplace transform that capital Y of s, which is now the inverse Laplace transform of 1 over s squared. And that, I hope, if you look at your tables or actually compute the inverse Laplace transform of that expression, you now see that that's this ramp for non-negative values of t, and it's 0 for negative values of t. We can conclude then this session by saying that no matter how we found the final answer, y of t, either analytically or graphically or by going into the frequency domain, all three of those analysis methods yielded, or we were able to find, the same result. So all three analysis methods yield the same result, which is a good thing. That means all of our approaches were consistent, and that then allows us to conclude this particular session.